So good afternoon, everybody. I will continue with dense graph limits. So I'll briefly recall definitions from last time. What we're interested is you have like a big unknown graph G, and imagine for every like small graph F, you have like statistics, how frequently you see F in G. There are many definitions which are more or less equivalent to each other. So I'll be using mostly this one, homomorphism density. So it defined as follows, the same definition as last time. So you look at all possible maps from vertices of F to vertices of G, and you allow two vertices to be mapped to the same point. It's fine. They're not necessarily injective. And then this density is probability that every edge of F, here xy, is mapped to edge of G. So you ask, if you take a random map, how likely it is to be a homomorphism. Homomorphism meaning mapping edges to edges. And then we say you have like sequence of graphs. Okay, so whenever I write a sequence, I mean the numbers of vertices increase, tend to infinity. And we say, so what we do, we say sequence converges if for every f like triangle pass fixed graph, if you look at its density, then it converges to some limit. So, and we denote it phi of f. So for every f, you have this limiting value. So in this way, a limit, this phi, it tells you for every fixed f, what is its frequency. So it's some function from graphs. We take them up to isomorphism into real numbers, or in fact, this would be interval 0, 1, because we scaled it to be probability. And then, another definitions we made last time, we looked at all possible phi which can arise this way, for which there exists sequence of Gn with this property holds. Yeah, so this is a very brief recap of Monday's lecture. Yes, if you have questions, please either write in chat, or if you can unmute yourself, ask. Is it okay? Good. Yeah, and then the question is, okay, so this is already useful for some problems, but still if you work with this set, at the moment it's just formally a set of sequences for every f, and then it's not clear how to prove some meaningful theorems. How is it useful? And this, in one way to think about this, you can imagine this quantity, like frequency of f, as some kind of moment. So like one analogy would be the Hausdorff moment problem. When you have some sequence of numbers, which kind of hypothetically is a sequence of moments of random variable, and you can ask, yeah, which ones are realizable or not. And this is like very similar situation. So in the Hausdorff moment problem, you have one measure on interval 0, 1, for which sequence are moments subject to some conditions. And so here limit objects will be a bit more complicated. So in this lecture, I'll try to define them and maybe convince you that they're useful, in particular in extremal graph theory. So our next section will be about graphons. So this approach basically was introduced by Lowas and co-authors, but of course, even in 70s, there were like some results in this direction. But main kind of, they started to study systematically about 20 years ago, and they coined this name, which is kind of some synthesis of a graph and function. And now it's like standard in this field. Yes, so our objective would be given some admissible sequence like phi, yeah, to construct some analytic objects which gives you the sequence. So first define a kernel. So by this I would mean a measurable bounded function which is from interval 0, 1 square into real numbers, which is symmetric. And symmetric means, okay, maybe let me call this function W. So symmetric means if it has two arguments, two real numbers. So if I swap them, the value doesn't change. Yeah, and measurable, I don't want to go into technicalities of defining what a measurable function is. Formally, if you take any interval and take its pre-image, then it's a Lebesgue measurable set, which basically means if you can consider various integrals involving this function W, each would have some well-defined value. Like you can integral W or functions involving W. And bounded, it means that its values, ignoring like some exceptional set of measure zero, are bounded. Or just say exactly bounded. So it means there are some values are between, say, minus million and plus million. So that's a kernel. And basically terminology comes from functional analysis because people use like two variable function for kernels. And in fact, sometimes in this area, it helps to view at these functions as kernels or as integral transforms. And then a graphon. So it's a kernel whose values are limited to 0 and 1. So for every xy, w evaluated at xy is between 0 and 1. And so maybe one analogy, if w assumes only 0 and 1, but not intermediate values, you can imagine it as a huge graph on unit interval, where 0 or 1 tells you if points are adjacent or not. And symmetric means exactly that if xy is an edge, then it doesn't matter in which order you take x and y. And then I define two spaces. So Kelly W, it will be a space of all kernels. And this will be convenient because it will be a vector space. So if I have two kernels, I can add them up and multiply the constants. And so if we define some norm, it's convenient to define it on space W. And then again, standard notation in this area, in particular in Lova's book, now Kelly W0 is a set of all graphons. And this W0 will be exactly where our limits will live. So maybe some examples of graphons. Yeah, you can just take a constant function, it's perfectly fine. Or you can take any polynomial, say x times y symmetric, as long as its values are between 0 and 1. Or it doesn't have to be continuous, so you can say something like maximum x minus y, and let's maybe just write it differently. Say indicator function that x minus y is at least 1/2. It's also graphon. So yes, so when people graphically write graphons, they try to use matrix notation. So in matrices, okay, row are indexed from left to right, and columns left to right, and rows are indexed from top to bottom. And somehow in this area, it seems also when people draw graphons to use the same kind of notation. So vertically, if you go down, values increase. So for example, the last one would be graphon. So this is diagonal. And this is graphon, which is one on these two triangles. Maybe I'll use different color. So here it happened to have value 1, and everywhere else it's 0. So these are examples of graphons. So they don't have to be continuous, but they have to be measurable functions. And basically, whatever function usually you come in analysis, it's always measurable. It takes some effort to construct a non-measurable one. Yeah, maybe some non-examples. So one would be like x plus y. It's not an example because its values are more than 1. Or for example, if you take, say, a maximum of, say, x minus y is 0, it's also not an example because it's not symmetric. If you change x and y, value changes. Mhm. Mhm. Good. So are there any questions? Let me just pause here because there was a whole screen full of definitions. So key definition is graphon. So it's a function on unit square, where at each point a value is between 0 and 1. And like adjacency of a graph, it has to be symmetric. So if you change x and y, a value doesn't change. And now, given a graphon, I want to produce some vector of densities, this function phi. And so I have to define what is density of a graph f in graphon. So here is next key definition. So homomorphism density, or just the density, of some graph f. Okay, now it would be convenient to label vertices of f. So maybe I'll just label them by 1 to k. So Kelly fk, by definition, it will be all graphs whose vertex set is interval 1 to k. So if you remember, this means yeah, I denote it as bracket k. Mhm. So you can use f of k as a labeled graph. So in particular, number of graphs in f of k is 2 to the k choose 2. Mhm. So when talking about densities in graphons, it would be convenient to look at little capital F as a labeled graph. Okay, so given a graph on 1 to k, its density, I'll use the same symbol T inside graphon W. So by definition, it's the following. So I integrate over, I pick k points, x1, xk, inside 0, 1. So let me write it in front, maybe it'd be more natural. So they come, each one is from unit interval, and they're uniform and independent. So you pick in the uniform element of 0, 1 to k. So for each vertex, you put some xi, and then, okay, I'll move it a bit down. And then the function which you integrate, so for every edge, for every pair ij, which is adjacent in your graph f, we take product w evaluated at xi, xj. So I thought there are some analogy with moments. So yeah, here is even more clear because we wrote it t of f in w is integral. So maybe let's look at some examples and hopefully it'll be clear what this definition says. Maybe like in very simple case, if I have K2, which is an edge, what is its density in W? Well, I just integrate over xy. I have two vertices, wxy, dx, dy. So kind of edge density in a graphon is basically its average value. Now, if I wanted to compute density of a triangle, then I would have also that, and I would have like a triple product, wxy, wyz times wxz, and so on. And here is like main result theorem for one, which was proved by Lowas and Sagedi. Published in '06. It says, okay, so for every W you get these moments or densities. And then it says the ones which come from finite graph are exactly which are realizable by some graphon. So if you look at this set of lim, maybe I'll go here back. So what is here? We look at all possible frequencies which come from some growing sequence of graphs. And a theorem of Lowas and Shakedi says, yeah, these are exactly ones which can be realizable by some graphon. So in other these such functions, you can describe as densities of f in W, where W is some graphon. Yeah, so it's quite non-trivial theorem. So I'll just sketch proof of easier direction. But is everybody happy what we're trying to prove? So basically there are two parts. Like we say two sets are equal. So one part which is harder is if I have a growing sequence of graphs and the frequencies of graphs converge, then there exists this W which captures this limits. And in the other direction, if I have a W graphon, then I want to construct a sequence of graphs that converges to W. So I'll just sketch a proof of the other direction, which is that for every W is kind of, you can realize it as a limit of graphs. So last time we had a theorem which described set lim. So this direction, you can check it that this theorem applies. So somehow if you define this phi of W to be equal this home density function, then you can check that it's normalized. Which, if you remember, it means that if you evaluate it on a graph with one vertex and no edges, then it should be 1. And it's indeed true, because if you don't have any edges, yeah, then in this formula on the top, this product is empty, so you just integrate function which is 1. So it's indeed 1. So you just take integral of function which is identically 1, so it's indeed 1. And also it's multiplicative. This the definition we had before, which was saying that if you take a union, disjoint union of two graphs, maybe f and h, then you want a result to be product of their frequencies or densities. So maybe let's see why it holds. So if I just scroll back a bit. So if so in this formula at the top, yeah, my f is now union of two graphs, f and h. So if I look at this, so I have two parts with no edges across. So if I look at these products, I can group all xi's, ones which come from the first graph and the others which come from the second. And then this product is just a product of two functions where two factors first depends on the first group and the other on the second. Yeah, and if you integrate product of two functions in disjoint variables by Fubini-Tonelli theorem, you can change integration in any order you want. So you can integrate first group and then second group, and the result will be just product of two integrals. So if you want to check that this function satisfies multiplicativity, yeah, then this is just consequence of Fubini-Tonelli theorem. That this function which we integrate is just product of two functions in disjoint sets of variables. Yeah, let me pause for a few seconds. Yeah, checking, there was one more property. So what we wanted to check was that if you define this upper Mobius transform, so I'll recall formula in a moment, it has to be non-negative. So, and the formula was that I take summation over all graphs f prime, which have the same vertex set as my graph f, but has perhaps some extra edges. So over all such choices of f prime, then I'll need probably more space. Then for each one, first I have like a sign factor -1. I just see how many extra edges I added. And then I have to multiply by density of f prime. So let me write it right away briefly as integral. So I integrate function, which is product over all edges in f prime of w xi xj. Okay, I don't write the bounds or variables, just very briefly. So, and one property which we had to check is this is always non-negative. So let's contemplate this expression. So how can we reorganize it a bit? So here we have integral and finite sum. So clearly we can exchange them. So we can integrate over sum of the terms. So maybe let's write it. So this will be integral. Okay, let me write it carefully because I'm going to use this as a definition. Then I have variables dx1, dxk. And then here I have basically products over all ways how to add edges to f. But each one is given plus or minus sign. So first one observation, if ij is edge of f, it's always included this factor wij. So I can just factor it out. Yeah, this is merely because in every product in the line above, if I have edge in f, it's also edge in f prime. So this is f prime. And then what remains, I have some products over all possible combinations of non-edges, and each one is minus sign. So, and then if you stare it for a few seconds, probably you'll notice that you can rewrite it equivalently as a product over all non-edges in F. 1 minus W of xi xj. Because if you expand this product, then you would get possible products of W non-edges, and also signs will be correct. So if you have no extra edges, then sign is +1. yeah, and so on. And now it's clear that this is non-negative. So like we checked like these three sufficient and necessary condition, but this quantity is quite interesting. So I'll this whole big integral. So I'll denote is as induced density of f in W and use symbol T induced. Mhm. So we basically we check two conditions. So the three condition of theorem 3.2, and then it implies that this phi W is indeed in the limit space. Mhm. But if you work with graphons, it's actually be easier to see it from what we wrote. So somehow I would like to prove, at least sketch of a proof of this implication without using theorem 3.2. So theorem 3.2 had necessary and sufficient conditions, but let me try to argue it a bit differently. And the proof will be similar probably to what you saw yesterday at practical class. I believe Riley proved that if you take random graphs, they converge to a function which is quasi-random limit. So here again, given W, we would like to construct some sequence random graphs such that with probability 1 as a whole sequence, it converges to W. So what would be like a random sample? So what we're trying to do, given W, I want to construct sequence of graphs. This will be random graphs. And I want them to be very likely to be convergent to W. So what is, how do we define it? So we given graphon W, we given some number n of vertices. So this would be some distribution on graphs with vertex set 1 to n. Mhm. So this will be a graph, random graph in Fn, i.e. with vertex set 1 to n. And definition would be, I would like to have, so this could be as a definition. So just to define a random graph, I want to give you a probability to see any particular graph. So probability to see, say, any given f, I would like to be exactly induced density of f. So here's a formula on the top. So these numbers are non-negative. And also you can check that if you add them up, you get 1. So with some probability. Mhm. But in fact, since we have graphon, if you look at this formula, actually you can see a different, more natural way how to sample this random graph. So what happens, how do we get this f? Basically, we take, so we want to see f for this probability, which is the top line on the slide. And if you look at this formula, actually it guides you what could be your sampling. You pick, okay, so here I change n to k. So you pick n vertices in 0, 1 independently. And then for each pair ij, you make it an H with probability exactly Wij. So for every pair, if it's an edge, then this is probability you rounded it correctly. And for every non-edge, probability that you see exactly non-edge would be 1 minus wij. So maybe just to keep it all on the same slide, let me write the same procedure. So differently. So we pick x1, xn in 0, 1, uniformly independently. And then we make I and j adjacent. So put an edge between I and j with probability exactly wij. wxi xj with all choices being independent. Mhm. So this gives you another way to generate the same random graph. So you
Sorry,
pick
I have a
an
question.
arguments x1, xn, and then you are guided by a value of w, how likely you make it edge on an edge. So for example, if w happens to assume values only 0 and 1, then xi determine the graph right away. Because just if value is 1, you put edge. If 0, non-edge. For example, if w is, say, constant 1/2, then, well, positions of xi doesn't matter because w is a constant. In this case, every pair you make an edge with probability 1/2. So this is exactly Ardyush-Rényi binomial graph, which we looked. So there are special cases. And but in general, you get inhomogeneous random graph where you have like, you can imagine positions in this interval is a type of a vertex. So if function is not constant, different vertices have different properties. And then W tells you how two vertices of a given type are likely to be connected. So if W is constant, it's homogeneous model. When all vertices are the same, maybe, so.
We have a question from the
Yeah.
audience, right? The question is,
Yeah, very
shouldn't
good
we check?
question. Yeah. So is it true that if you add this, so I wanted make this the probability. Is this true that it sums to 1? Yeah, if you add it up and do some formal algebra, things cancel, you would get exactly 1. Or equivalently, you can kind of, maybe it's easier to see equivalence of these two random samples. And then it's clear that this means some probability because all these f, they exhaust all possible outcomes. Yeah, this has to be checked. So one way to do some formal algebra, or another way just to see that these two random models are equivalent. Mhm. And okay, and so now we would like to argue, I won't prove it, but so for each n we have random graph. And we would like to show that they converge to W. So maybe as the one step, I just compute expectation. So what I do, so I generate this random graph with n vertices given W. Then I want to look at, say, induced density. Okay, let me look maybe easier, injective. Okay. Okay, let's do induced of f in WG. So what is this expected value? So here, so I have some graph f with k vertices. Okay, now it has k vertices. So if you remember, what is definition of induced density? So in my big random graph, I have to pick some k vertices, and this definition requires my functions injective. And then this is, I ask, what is the probability that on these k vertices I see exactly f? But if you look at the sampling as written here, all I care what I see on specific k vertices, so I can ignore all the rest. So basically this expectation will be exactly induced density of f in W. So exactly what we wanted. So at least an expectation, if you fix any W and you generate random graph, then for every n, expected value is what you want to see in the limit. And then you have to apply some concentration result. You want to argue that it's very unlikely to deviate from expected value. So, so you want to apply some concentration result. And one is, for example, Azuma's inequality or bounded differences inequality, which says if you look at this random variable, so randomness comes from this graph. Then if you change like one xi or rounding xi xj, this function changes by tiny bit. Because if you change some vertex xi, well, first you have to hit with image of f this xi, which has probability k over n. And then like Azuma's inequality shows that they are very unlikely to deviate. So this implies that with probability 1, I won't give details. So if you take, if you generate Gn from with this random model independently, then sequence Gn converges to 1, to W. So this is like a very rough proof sketch of convergence. And so what do I mean converge? Let me just write. So sequence Gn converges to W. It means for every f, density of f in Gn converges as n goes to infinity to density of f in W. And in this definition, if you want, you can replace density by induced density. It wouldn't change. So maybe let's look quickly at some examples. Similar ones which we looked last time. So if you take cliques, then every two vertices are adjacent. So they converge exactly to constant one graphon. Like empty graphs, they converge to constant zero graphon. Quasi-random to constant p. So maybe look, it's a bit more, slightly more subtle case, but still. So suppose I looked at complete bipartite graphs. So I have two parts almost equal, and I put all edges between them. So how can I write limit as a graphon W? Well, I can partition my interval into two parts of measure 1/2, because these two parts are half of vertices each. And then, so again, if you remember, diagonal goes this way. So it's 0, 1, 0, 1. Yeah, and then I define W to be 1 when they come from different parts. So one vertex in part 1 and the other in part 2. So these are the values when I'm 1. Okay. So for example, what will be a random sample from this graph? Basically, I have like two types of vertices, first half or second half. So I pick each one at randomly, and then this graphon assumes value 0 or 1. Then I put an edge if and only if they come from different parts. So my random graph looks like complete bipartite graph, except part sizes may deviate a bit from one half, but it still converges to what I want. So if I take this graphon, yeah, sampling would be basically complete bipartite graph, except part sizes could change a little bit. So maybe here's another example. Suppose I take, say, blow-ups of a path. So what would be the limiting graphon? Well, I have like three types of vertices. Again, here inside parts, I don't have any edges. So I put zeros. And then maybe parts are 1, 2, 3 in this order. So then I have edges between 1 and 2. So here I put value 1. And then between 2 and 3. So here I put value 1. And everywhere else it's 0. So what I would get is if I take blow-ups in this 3-vertex graph, I have like 3-step graphon. I have a 3 times 3 grid, and the value is constant. Now, if I, for example, change it a little bit, maybe like I decide to put click inside part 3, yeah, then here I would put also value 1. Or if I decide to put some quasi-random bipartite graph across 1 and 3, maybe density 1/2. Yeah, then between part 1 and 3, I would put 1/2. But in general, yeah. So if you have some sequence of blow-ups of a graph G, which means I start with G, I replace each vertex by 2, then each vertex by 3 copies, and so on. Then what they converge, so suppose G has k vertices, then basically I partition interval into k equal parts. I may take as well intervals, and then here I put adjacency function of G. So on diagonal it will be zeros. And everywhere else I put 0 and 1s to denote adjacency. So this graphon I'll call W of G. So for example, what would be my random sampling from this W of G? Well, suppose I want to sample a graph with m vertices. Then I pick m uniform x1, xm from interval 0, 1, but since parts have measure 1 over k each, it's the same as I'm just pick uniform vertex from G with repetitions. And then I connect vertices if they're adjacent in G or not. So sampling from a graphon amounts to sampling from a graph. So yes, it may be good to think. So if you have a graph G, then k sample from G would be I pick k random points with repetition, and then I connect them guided by G. And then sampling from graphon is like some kind of a limit version of this process. Mhm. Mhm. Okay, yeah, I wanted to move. Yeah, I'm running so much behind schedule, so I'll try to maybe just give one or two definitions and maybe say vaguely what graphons are useful for. And then I wanted to talk about different kind of convergence so that like you can work on homework too. So maybe let me just mention some important things. So first one, like uh, clearly if like in graphs, if you relabel vertices of a graph, it's combinatorial is the same object. So same applies to graphon. If you can take any graphon, in principle you can replace relabel number between 0 and 1 in any measurable way. So that's kind of be aware. So this graphon is not unique. So if you take any measure preserving map, maybe call it psi, from unit interval to itself. And if you have graphon W, you can define its pullback, called W psi. And how do we define it? So one way to view it is just you relabel kind of vertices. So psi tells you the new labels. So you evaluate W at psi of x and psi of y. And you can check it's still a graphon. So it requires a bit of technical checking. It's clearly symmetric, and then you have to check other properties. And one property is that if you look at densities of f in pullback, then it's the same as in original graphon W. So you can easily generate different graphons which have the same frequencies. And also beware that this measure preserving map, it doesn't have to be bijection. So for example, you can take psi, which maps x to 2x mod 1. So its graph looks like this. It's measure preserving because if you take any set A, its pre-image is just 2 copies of A scaled down by factor 2. It has the same measure. And then what is W psi in this case? Well, again, if you draw a picture, then you partition your interval into square into 4 parts, and basically you put copy of W inside each part. And these two graphons have again the same densities, so they're equivalent. And then important result by Borg, Chase, and Lowas says that's all what you can do. So if two graphons have the same densities, then essentially that's all the freedom you have, how you define a graphon. So yeah, there are some technicalities how to state this result, but yeah, okay, if you want to look at, yeah, I would refer to Borg's, Chase, Lowas. Mhm. Yeah, and another definition I want to make. Okay, so somehow when I started lecture course, I said you look at finite graphs and you define some notion of distance or similarity. And then we looked at these vectors of frequencies, and we took like pointwise topology. So you can define artificial distance by kind of saying photographs are similar if these vectors are similar. Yeah, so you can make it up, but much more natural is this so-called cut distance. So I needed to define in a few steps. So first I have to define cut norm. And so I want to compare how two graphons close to each other. So, and in this case, I just take the difference and say norm is small. So I have to define for kernels. So cut norm of a kernel W on box norm, it's denoted norm sign and then little box. So by definition is the following. I take any two measurable subsets of 0, 1. Then I integrate over the product my value of W. And I ask how far I can deviate from 0. Because if W is 0, then this norm is 0. But maybe W, say, assumes values plus and minus 1, like randomly. It deviates a lot, fluctuates. Then in this case, yeah, norm could still be small. Mhm. Then here, you can, there are some different variations. You can ask SNT disjoint or intersecting, but these variations, they give you basically within constant factor the same norm. Mhm. So maybe let's see what this norm tells for graphs. Suppose I have two graphs G and H, which have the same number of vertices. Say a vertex set is 1 to n. Then basically, so I take, okay, each little, so if you remember graphon of G or H, I partition big square into n square little squares. So each one contributes 1 over n squared to integral. And then I take supremum over set S and T. So this is not precise, which are subsets of n. So what is this integral if I take this adjacency function? Well, it means I just see this two graphon, this difference of two graphons, it's either +1 or -1 or 0. So this will be exactly number of edges in G between S and T minus number of edges in H between S and T. This formula is not quite correct because in this top definition, like S and T could split vertices into parts. So kind of this, here I would take some fractional version. But again, within some, if you care about going to 0 or not, then these are equivalent definitions. So somehow when two graphs are close to each other, so I have two graphs on the same vertex set, H and G. And this definition says whatever I take two sets, S and T. So here I just drew them disjoint to make it easier. So they're disjoint if when I count number of edges in G between them, and I count number of edges in H, then these counts are close to each other for every S and T. So for every cut, I see approximately the same number of edges in both. So like a special case when S and T a partition, so it's a cut of vertex set. That's where the name comes from. Yeah. And finally, I can define a cut distance. Again, I'm just guided by principle that, well, if I relabel a vertex set, graphon doesn't change. So distance between two graphons would be, I just take a cut norm. Where one of the graphons, I can apply any map F. and I want to find a map psi, which is kind of optimal, so it'd be infimum measure preserving psi from interval to itself. So for graphs, definition would be two graphs are close to each other. First, you can scale them to have like same weight, vertex weight, say 1. Then you use psi to put one on top of the other. And then this distance says that distribution of edges across cuts is about the same. Yeah, I know it's a bit vague, but like one important property is so-called basically I just stated, so convergence in cut distance is equivalent as usual home density convergence. Again, there are like two directions. One happens to be rather easy, this counting lemma, that if two graphs are close in cut distance, then they have the same frequencies of smaller subgraphs. Yeah, and the other direction is quite involves some work. So, uh, so maybe to wrap up this section about graphons, so let me just say a few very high-level comments. So for me, like my interest was that graphons you can use in extremal graph theory. So you have some extremal problem. For example, for every n, you can take an optimal graph, unknown one. Then you take the limit, some unknown graphon W, and perhaps, yeah, you can, it's space compact. Okay, it's another result which you have to prove separately for space of graphons or derive from equivalence to home convergence. And then instead of studying larger and larger graphs, you can kind of try to study this limiting graphon. And what advantages you might get, in some sense, you can apply differential calculus. So you know it's the object which exactly maximizes your function. So if you perturb it, you cannot improve it. So this was used as Borel, for example, to solve a triangle problem. But then usually when a finite extremal problem is solved by a limit approach, in most cases you can prove transfer proof in finite universe. You don't need to appeal to graphons. Like in extremal combinatorics, people were very good in kind of making all this differential calculus arguments precise, like you change edges or you apply improving induction or whatever. But still, it's a very great tool for kind of intuition and for proving results. Yeah, and now many papers, when they prove results in finite combinatorics, some of them are written in graphon language because it makes proof cleaner and easier sometimes. Not always, but sometimes. On the other hand, there are some applications where you really need graphons. Maybe just one example would be large deviation principles, LDP. So again, for example, you can take just basic Erdős-Renyi model when you sample n points and make two points adjacent with probability p. And then, okay, we know density of triangle about 1/8. But then you can ask question, how likely you see density of triangle more than like 1/2, which way off. And so, and to answer these questions, one way is to have some topological space. Then events which are interested would be like Borel subsets, like number of triangles or Borel functions. And then you can ask how likely you see any particular event. It would be to maximize in so-called rate function. Yeah, and to develop this theory for random graphs, in particular for homogeneous one, but for any other models, actually space of graphons is really is the one which is used. So LDP theory for random graphs. So it needs W0 as the kind of underlying topological space. So, and yeah, this is like one example where you really need this analytic representation of graphons. So this was a breakthrough by Chatterjee and Varadhan. I think published in 2011. Yeah, so probably this finishes lecture for today because we are a bit over time. So we can stop recording.